Okay, guys, so here's an example for number 7 on today's classwork. The first thing that we're going to do is we're going to take a negative out of the denominator. Which will change all the signs in the bottom. The reason for that is because this is a completing the square type problem. And when you're completing the square, you can't have any coefficients on your x squared. It has to just be an x squared. All right, the next thing that we're going to do is we're going to group the x squared and negative 8x, leaving a little space here. And we're going to actually create another little space over here after the 20 as well. And the space is for the process of completing the square. It's where you take half of the 8, which is -4, and then you square it, which is 16. And that's what I'm going to add in here. And we're going to put a -16 on this side. And that way they kind of cancel each other out, so it's like they're not really there. But we do want to see them there. So that's that. And now we move on to the next step, which is to factor, this. Now, when you factor a perfect square trinomial, which is what we just created by completing the square, it's always going to end up looking like this. The only thing that's going to change is the number that goes there. Okay? And so that will always be half of that middle number there, so it's going to be x minus 4 squared. And then we're going to combine these together as well to get 4. All right, at that point, we're ready to go ahead and do the integration process. We're going to let u be equal to x minus 4, which means that du dx equals 1, which means that du equals dx. And this is an arctangent pattern. And so we're going to have negative arctangent of u over 2. The square root of u squared is u, and the square root of 4 is 2, so it's u over 2. And we also put a 1 over 2 in the front. It's 1 over whatever this is, right? That's your a value. And then, of course, we put the u back in that was there at first. And so my u value is x minus 4. All right, and so that's how you will handle that one. So that's kind of how those problems where you have a trinomial on the bottom and then just a number on the top, that's how those will be integrated. Let's go ahead and move on to question number 8. We're skipping 8, so let's move on to 9. Number 9 is a long division problem. So the first thing we're going to do is we're going to do the long division. The polynomial on the top goes inside the division bar. And then the polynomial on the bottom goes out here. And we ask ourselves, what would I multiply this by to get this? And the answer is x. So I'm going to put an x over here. And by doing that, I'm going to get x cubed. X times x is x cubed. And then we also do x times -1, which gives me negative x. Now I'm going to put it underneath of that 5 there because you want to line up your like terms. The next thing we do is we go ahead and distribute a negative, which changes these signs. And then we add down. So this is going to cancel. The negative 4x squared can come down. The 1x and the 5x can make 6x. And we can bring down the 3. And then we repeat that process. So now we ask ourselves, what would I multiply x squared by to get negative 4x squared? And the answer is -4. So if I take that 4 and multiply it times both of those and put my answers underneath, I will have the following. Changing my signs, I would get positive here and a -4 here. And these cancel. And I'm left with a 6x here and a -7 here. All right. Now, that's my remainder. As soon as you end up with something here that is has a power less than this one, you're done. And so now this integral can be rewritten in the following fashion. We have x minus 4 is what we got from the division. And then we have our remainder over the divisor. Okay. All right, so let me erase all my extra work here now. That's the long division process. The next step is to integrate. So I'm going to separate these things. I'm going to integrate this, and then I'm going to integrate this separately because they require different integration rules. This first one is a simple integral. You just do add 1 to the power and divide by that number. And then for the 4, you just put an x next to it. As for this other integral over here, that's going to require some work. Now, for me, it's going to be u substitution. But I think I'm going to, and actually mine might not even integrate very well after this. So I'm going to stop here with my problem. Now you guys will need to still evaluate this, but for you guys, I want you to be aware of something. On the example I have in our Unit 6 review notes, this turned out to be an ln problem. However, for you guys, since you're going to have a square down here, yours is actually going to turn out to be an arctangent problem. So I'll give you that little hint there. This one is not an arc, mine's not an arctangent that I'm working on right now, but yours on the one that you're going to be doing is. So just wanted to give you a heads up, it's not a natural log. All right, so I'm going to go ahead and move on for number 9 here at this point and take a look at number 10. So what this question here on number 10 is asking us to do basically is just to make sure that you understand the properties of integrals. So let me tell you why B is a tempting answer choice. As you guys are looking at this, you're thinking 2x to the third plus 1 squared. Well, isn't that the same thing? It's just 2x to the third plus 1 times 2x to the third plus 1. And therefore, can't we just distribute the integral to each one separately? And the answer is no, you can't do that. There is an integral property that says that if you have two functions being added, that you can separate the integrals like that. But there is no property that says that if you have two functions that are being multiplied together, that you can integrate those separately. We don't have a rule like that. So that's actually a trick question there. That's not allowed. Another tempting thing to do here is to notice that this inside portion looks like a u, doesn't it? The problem with treating that like a u, however, is going to be in the fact that once you take the derivative, you're going to get 6x squared, and then you get the dx by itself. And so whenever you put this in here, yeah, you would have u squared when you put it in here, but you should have du over 6x squared here, and it's just not there. So even though that was a tempting one, you might be tempted. And yet, to take it even further, some of you guys may think, aha, well, there it is. But that's actually not the answer either. And the reason for that is because even if you did have an over 6x squared here, you're allowed to take the 6 out, but you can't take the x out. That's not allowed. You're only allowed to take out numbers. You can't take out variables when you're doing integration. So that's not allowed either. So the answer is obviously A, but I'd like to explain to you why the answer is A. The answer is A because of the fact that 2x cubed plus 1 squared, it does mean that we have 2x cubed plus 1 times 2x cubed plus 1, but we're actually going to have to FOIL this out to see why this works. And by FOILing that out, doing the first, outer, inner, and last, we can find that that is a true statement. And so instead of trying to do u substitution or splitting up the integral, really we could just FOIL out the expression and come up with a much simpler looking integral that way. And so for this one, the answer is A. So this was really meant to be like a tricky question because they want to make sure that you don't commit some math errors that are tempting to make because they seem like, oh, that seems like a good move, but they're really not. This can't be the u because it's missing the 6x squared. This can't work because you're not allowed to take variables out of an integral. This one can't work because you're not allowed to distribute an integral over multiplication. This is the only option that works. All right, so let's go ahead and take a look at number 11. So this is a U sub problem. So just basically see if you guys can figure out what the U is. After that, I think you'll find that it's a pretty straightforward question on number 11. Let's take a look at number 12. Number 12 is a weird looking problem. I've seen these a few times. It's U sub. So what do you guys think the U would be here? You guys hear the birds in the back. All right, and then we'll go ahead and find our du dx. Now the derivative 4 goes away. The derivative of ln is 1 over x, but there is that negative in the front, so we have negative 1 over x. And now we want to get dx by itself, so what I would do here is I'd multiply both sides by x. Then I'd multiply both sides by dx. Oops. Technical difficulties. There we go. And that's going to cancel out the dx's on this side. And then just divide both sides by a negative 1 and you get the following. Now we're ready for our U sub. So I've got 5 over 2x, and I meant to put a square here, and I needed to have a dx here, so I left some pieces off of there. But all right, back to the problem. So my U is everything in the parentheses there, and my dx is negative x du. And now in this case, the x's go away, and we can also take the 5 and the 2 and this negative out because those are all just constants. So I could slide those out to the front really quick. And that leaves me with this, which is a much nicer looking integral. But we still need to change our limits. We do have some limits here. E to the 4th is one of them. So we're going to take that and plug it in here. So if u is equal to 4 minus ln of e to the 4th, ln and e basically just cancel each other out. And so you're left with 4 minus 4, which is 0. So my top number is going to be 0. Then we're going to plug in 1. Ln of 1 is 0. So that means the bottom number is going to be 4. Okay, and so at that point, we should have a pretty simple integral to work with. And we'll just go ahead and finish it up now. Oops. Oh well. I'll just delete the whole page and then we'll start over. So we have the integral from 4 to 0 of 1 over u squared du with a negative 5 over 2 on the outside. All right, so the first thing we're going to do this integral is we're going to rewrite the integrand a little bit. We're going to change that to a u to the negative 2. Next, I'm going to add 1 to the power and divide by that value to get my integral, which is u to the negative 1 over negative 1. And we're going to carry our limits down here, like so. Before I plug in my limits, I'm also going to rewrite this piece a little bit. The negative power on the u causes it to move to the denominator. And instead of just having the bottom be negative, I'll just make the whole thing negative here. And so we go like that. Okay. Next thing we'll do is we'll go ahead and do the process of plugging in and subtracting these things. So if I plug in 0, I'm going to get undefined there. And then here, 4. Now, this is because I made up my problem and I wasn't very careful. I ended up with an undefined here. So there's actually no solution for me at this point. So we'll leave it at that. But for you guys, it's going to work out. You're not going to get a 0 there. So we'll go ahead and let you guys handle it from there because I can't go any further since my problem turned out to be a little bogus. But the good news is that was all the hard stuff. So just doing U sub, and that'll do it. Let's go ahead and move along to the next part, which is the FRQs. All right, guys, so this is our first FRQ. They give us this function here, and they want us to estimate the value of this integral using a midpoint Riemann sum, and they even tell us what values to use. The only thing that's kind of weird about this is that they don't put it in the form of a table, which we're used to seeing, but we could fix that to make it look a little more friendly. Maybe you can do it without the table even, it's up to you. I'm going to do the table just so it looks familiar. So we have 1, 1.6, and 2. Now when you do a midpoint Riemann sum, you're going to want to leave some spaces in between because we really want the midpoints, right? Now I don't really care about the y values, but I'll go ahead and put them in there anyway. Well, actually, no, I won't. We'll skip doing these because we don't care about those. We only care about these y values, the midpoint y values. So let's go ahead and find our midpoints here. So how do we do that? Well, if I want to find the middle number between 1 and 1.6, basically what I need to do is clear my page first, and then I need to bring up my calculator, and then I need to do 1 plus 1.6. Add those two numbers together, and then divide that by 2. And that'll tell you the middle number. So the middle number is 2.3. So we're going to put 2.3, wait a minute, not 2.3. It was 1.3, wasn't it? Let me look again here. $1.3, not 2.3. That makes sense. All right. 1.3. And then we're going to repeat that process for this one. That would be 1.8. All right. Now we want to find our y values. And this is where the graphing calculator is going to come in handy because I don't really want to figure out what's cosine of the square root of 1.3. So let's go ahead and go to our calculator and plug in these two values here. So we're going to do cosine of the square root of 1.3. That's one of them. And then we're also going to do cosine of the square root of 1.8. And that's the other one. So let's go ahead and write those numbers down. Matter of fact, instead of writing those numbers down, I want to remind you guys how to store them, because every time you just write something down, you have to round it. And every time you round it, you lose accuracy. So instead of just writing down the outcomes, I'm going to go ahead and I'm just going to go ahead and store them. So to do that, you push this button down here, STO, and then you click alpha and you pick a letter. I'm going to go with A. So there's that one. And then we're going to do the other one now. So let's do cosine of the square root of 1.8. And we're going to store that under something else. So store that as alpha B. Okay? And so now when I come back to my work here, we're going to just put A here and B. Now, on a real FRQ, you would have to actually write down on your paper somewhere what those equal. I'm not going to because it's kind of hard for me to go back and forth between screens and I don't remember what they were, but there it is. But you do have to make sure you define them if you do that. But I do like that process of storing it instead of rounding them. All right, now we want to find the midpoint sum. So the way you do that is you find the length of your bases, which is the distance from here to here, which is about 0.6, and the distance from here to here, which is about 0.4. And what you're going to do is you can do base times height, and you get 0.6 times A plus 0.4 times B, and that will give us our estimated value of the integral. So let's go back to our calculator and do those things now. So 0.6 times alpha A plus 0.4 times alpha B. And there would be my midpoint Riemann sum. And we can round our final answer to the thousandths place, so 0.341 would be our final answer there. And so how would they be grading you on all of this? Well, I think that they would give you a point, maybe even 2 points for doing this table correctly, or at least finding the correct values, I should say. So did you get this point and this point correctly? And then they'd probably give you a point for this. So this question would be worth either 2 or 3 points. They might give you 1 point for the table and 1 point for this in the final answer, or they might give you a little bit more points for the table and this in the final answer to make it 3. But I think that's how it would be graded. All right. So let's go ahead and take a look at part B. All right. So for trapezoidal sum, we're using the same intervals here. So it's going to be 1, 1.6, and 2. Now we need to find the y values that go with these. So I'm not doing the midpoint anymore, so we don't need the midpoints. We actually just want to do the actual values that they gave us. Now, for me, I'm just going to call these A, B, and C. I'm going to let my calculator do it. And once again, if you're going to write those letters down on your paper, you need to write down what they equal somewhere on your paper, even though I'm not going to do that because, like I said, it's kind of a pain in the butt for me to toggle back and forth. So I'm just going to leave it like this. But after I find out what A, B, and C are, here's how you do the trapezoidal sum. These two numbers here would comprise a base of one trapezoid, or two bases, I should say, of one trapezoid, and the distance from here to here would comprise the height of that trapezoid. And so the formula for that first trapezoid will be the height cut in half times the sum of the bases. And then you're going to repeat that process for the next pair. So the next trapezoid will have these as bases, and the height will be 0.4. And so the next trapezoid will be 0.4 over 2 times b plus c. And then finally, you'll just go ahead and add these together to get your total answer here. And how this thing will be added, or graded, I should say, is probably the same way. I would expect maybe 1 or 2 points for this, and 1 point or so for that. I don't think that they would give more than 3 points for this one question. So it's likely they'll make it 2 points, but 3 is a possibility. But let's go ahead and actually do this on the calculator now so we can get our correct answer there. So bring up my calculator. Let me clear everything out of here. And we're going to start storing some values. I think this time I'm going to put the cosine function here just because I want to be fancy like that. So cosine square root x. There we go. That way I can use the y bars function instead of having to keep typing that function in over and over again. So we're going to plug in 1, and I'm going to call that A. Then I'm going to plug in 2. I'm sorry, 1.6 is what I was going to plug in. And I'm going to store that as B. And then we're going to finally plug in 2. And then we're going to store that as C. Oops, I didn't push store. There we go. All right, so my first trapezoid was, it had a height of 0.6 over 2, or a height of 0.6 divided by 2, times the sum of the bases, which was A and B. Then we're going to add to that the second trapezoid, which had a height of 0.4, and then we're going to divide that by 2, times the sum of the other two bases, which was B, and C. And there would be our answer, 0.344, if you round to the nearest thousandths place. Okay? All right, let's go ahead and take a look at our next one. So for part C, they tell you the first derivative, they tell you the second derivative also, and then they ask, will the trapezoidal estimate that we did, or would a trapezoidal estimate be an underestimate or an overestimate? Well, trapezoidal estimates are over anytime the function is concave down, because then whenever you draw your trapezoid under the curve, the trapezoid is less than the curve. It's underneath of it. Whereas if you have a concave up function, then whenever you do a trapezoidal estimation, the trapezoid goes higher than the function, so it's an overestimate. So actually I need to rearrange this. This is over. So that would be an overestimate, and this one would be an underestimate. Okay, so let's review. So a trapezoidal sum is an underestimate when your function is concave down, and it's an overestimate when your function is concave up. Now, when is a function concave down? Well, a function is concave down when its second derivative is less than 0. And a function is concave up whenever its second derivative is greater than 0. So that kind of explains why maybe they gave us this. They want us to determine whether or not the second derivative is positive or negative on the interval from 1 to 3. If it's positive on the interval from 1 to 3, then it would give us an overestimate. If it's negative, then it would give us an underestimate. Okay, so let's go ahead and how would we do that then? So now the question is, how can we tell if this function is positive or negative on the interval from 1 to 3? Well, I would say let's go ahead and graph it. Let's graph the second derivative. And if on the interval from 1 to 3, the second derivative graph is up here, well, that means that it's positive. So if the second derivative is above the x-axis, it's positive, which means that the second derivative is positive, which means that the function is concave up, which means that the trapezoidal estimate's an overestimate. But if my second derivative is down here, then that means that the second derivative is negative, which means my function is concave down, which means that the trapezoidal sum gives me an underestimate. So let's go ahead and see what it looks like. Now, it's possible that they're gonna really mess with us here a little bit, and they're gonna make it go a little over and a little under, and we'll have to think about that if that happens. But let's see. Let's wait before we predict that. So I need to type this function here into my calculator. Now this is not going to be fun to type, but so I'm going to put the whole fraction in parentheses for the first one. So it's going to be sine of the square root of x divided by, and now I'm going to put the denominator in its own little set of parentheses because there's a whole lot of stuff down there. 4x, and then we got a square root of x in there too. All right, and then I'm going to close the parentheses for that fraction. And then we have the next fraction, which is cosine square root of x over 4x. So let's go ahead and type that in. So that's minus, and then cosine square root of x. I know this is tedious, but I figured you guys would probably want to watch me put this thing in because it's a pretty difficult thing to type into the calculator. Divided by 4x. And once again, I'll put that denominator in its own little set of parentheses. And I think that'll do it. Let me make sure I got that right there. Yeah, we should be good. All right, so we're going to graph it, but I only want to see the interval from, I think we said it was 1 to 3. Is that right? We were only going to go from 1 to 3. I don't know what to adjust my height to, so I'm just going to leave it. All right, so as you guys can see, from 1 to 3, the graph is always underneath of the x-axis. Okay, so we're ready to give our answer then to this problem. So here's how we would answer the question. I'll type it out. Since f double prime is negative on the interval 1 to 3, that means f is concave down on that interval. And therefore, the trapezoidal sum is an underestimate. Okay, so there's that. Now some of you guys might be thinking, well, Mr. Bailey, what if they did give us one of the problems where it's not always underneath? Well, it would have to be really obvious, but I'll show you what they could have done. They might have done something like this. Okay, so in this case, if they did something like this, well, the amount of area that's under as opposed to the amount that's over is much less. So it's more of an overestimate than an underestimate in that case, right? But it would have to be really obvious. Or I guess they could be really mean and ask you to find where it crosses the x-axis and then figure it out. But I don't know. I think that's kind of pushing it, honestly. I think that this was more than enough. So that's part C. Let's go ahead and move on to part D. Write the integral from 1 to 3 as the limit of a right Riemann sum within subintervals of equal length. This is the thing that I said I never taught, and it involves this, and we're not going to do it. So I guess I didn't catch that whenever I assigned it today, so you guys can go ahead and just skip D. We're going to not do that one. Let's move on to our, is that it for today? We just had one FRQ. Nice. So I guess we're done. All right, guys. So that's it. Hopefully it was helpful, and we'll see you guys in class.